Hello guys. Hello guys. In last video we have seen what a graph is, how to represent it in terms of code, that is which data structures and what are the different formats we use or what data structures we use to represent a graph. Those were like adjacency matrix, adjacency list, and a form of it like array or using hash set. And then we also seen this compressed sparse rows, which are very good for caching a graph. And also we have seen uh, one more representation, that is hmm, what was it, just yeah, the incidence matrix where edges are the first class members. So we have seen all of this. In this session we will revise basic operations or basic problems on the graph we solve, and we'll be using recursion like naive intuitive approaches as we're starting up. uh, Later we will use stacks for those. You will understand like now. So if I say okay, mm, if you see, today we will be covering whether given a graph, whether we have a path from source node to a destination node, and whether given a graph we will be printing all the paths from source node to destination node, and later we will get the largest node, largest path from source to destination, and smallest one. This is in terms of number of edges. And then we will move on to this thing, largest path in terms of weights, and smallest path in terms of weight, and then kth largest path in terms of edges. We will be solving these on a basic graph. Let's just, without wasting time, start with, we have to check whether path exists or not from a source node to destination node, right? So what we will do, let's say we have a graph with A, B, C, D, then E, then F. Then let's say this is the graph and we have this. Okay. So we have to check whether a graph exists, path exists from A to source to destination, that is A to E. So how can we do that? New approach would be, if you guys are familiar with recursion, what we do is, at every step, let's say we are at A, I will ask my direct neighbors which I can reach, that is B and C, whether a path for E exists from U to. If this says yes, then I would consider as I got the path. As I can reach C and C can reach to E, then there is a path exists. Very simple. The same way, what C does, C also does the same thing. It just asks its direct neighbors, and one of its direct neighbor is E. So it got the answer. Simple. So this is the code for that. So this is a basic graph. We have like 6 vertices, and this is the inputs. Rather taking the input from the command line, what I have done is I have hard coded the graph edges here. So what I'll be doing, I'll forming a adjacent list uh, of like array, since we have nodes from 0 to n. So this is the most efficient data structure for this use case. So we formed a graph, that is adjacency list. And now whether we call this function and we pass source, destination, graph and visited. Since one more thing we have to notice here is that, let's say I am at here, right? See, since this is a graph which has no direction, C's direct neighbors are not only F and E, also A, right? So what it will do, it will first ask A, right? But we don't want to ask A because we just coming from A. So what we do in here is we maintain an track of what are the nodes we are visiting in a path, in a route. So what we do, when we visit A, we just mark visited of A as true. And when we are checking for neighbors of C, we check that the neighbor should not be visited. That is like, let's say here visited is like our graph has A, B, C and all. We can either, for simplification, let's consider A as 0, B as 1, like this. So we can just map it like, if I do A minus A, let's say this is 70 something, that is like ASCII number of it, character uh, character subtraction, so I'll get 0. So what I'll do, I'll just check visited of 0 should not be equal to true. If then only I travel to that neighbor, right? Visited of E dot neighbor. So this is how it works. So this is the like main insight here. So this is the function. So what it does, it checks whether we reached the node which is our destination. If it is this, it just returns true. If it's say, it just returns true, and then it marks the node as visited. Then it travels to graph of node will give all the neighbors of that node, because we have stored like this. A graph is just an array of array list where each index has an array list of that nodes which are neighbors of it, and first of that every edge in that array list, first member is node, and second member, that is neighbor, is its neighbor. So it just represents all the edges or connections of that node. So we just check it's not visited to avoid circling, or like to avoid that TLE or stack overflow errors, because it's keep on looping over two nodes. And next we call the same function with e dot neighbor. This stack of function calls will get us the answer, and it is called recursion. So if it's returned true, I'll just return true, otherwise I'll return path. This is the basic, very basic intuitive approach for finding whether a path exists between a node destination and a source node. And using the same logic, this is the code for it. Next, let's move on to this thing. You have to print all the paths. How do we do that? Now we know how to find a path, right? We just want to know, like, rather than just returning when we first, like here, right? If just when I get to reach E, I just return true. So all the other explorations of paths leading to E were just terminated because there was no need of it. Instead, what we will do when we will reach E, we will store the pass the path of that route. Like here we will pass A, so here we will pass A comma C, and we just add E, and we will store it in an list, right? And while returning back, we don't do anything. Next, we will explore this path. From this, we will reach. So we will again store A, C, F, E. Similarly, we will store every path. And here also, if you see code of it, it's like this. For print all paths, we don't have to store it. We just have to print it. See, if you see here, what we are doing, print all paths. We are starting with a source. See here, we're starting with a source, and this is a destination, and this is our graph, and this is visited array, and then it is this value of source. We are passing the source value as path so far. And what we'll do, as usual, this is the base case. When we reach the destination, we just print the path and we return. And first we mark node as true, as visited. Then we in graph, if visited is not true, we ask for printing all, we call the same function, which eventually leads to destination and prints path. And what we do after doing this, we just mark this node as not visited, because once we see here, what will happen, let's say I visited E once. If I don't mark it false, when I came back, when I back pop the function call from the stack, like when I print E, then I come back, when I return, come back, and this is again a path which leads to D, which again leads to F. Since F is already visited, I'll just traverse back. I'm not exploring that path again, because we are avoiding repeated visits of every node. But in this case, we want to explore every path, so repetitions must happen. So what we will do, we'll just mark it as not visited when we finish exploring the afterwards path from it. Understood? So that's very basic thing. We're just revising things. Okay, so this is the code for it. Very easy, very simple. Next, what we have to do is we have to print a path, or path which has most number of edges. Just right. Just now we found all the paths from source to destination. So we just need to find the path with most number of nodes, which will have most number of edges. Right? Very simple. What we will do, rather than printing paths, if you see here, what I am doing is I am just storing every path in a array list. I'm storing every path. I'm also storing a weight of that path. Why? Because I will be needing it to calculate the largest path in terms of weight. So I'll be doing this. So later what I'll do, when I call this function here, what I'll do, I'll created this thing. I created paths, which is a graph, which is like array list of graphs or a paths. Path is just a array list of integer, and all the paths will be a array list again. And then I have an array list of integer where each integer is a weight of each path, each corresponding path in this list. And then I have this path so far where I will store a running path of any route. So what I will do, I'll just get all paths. I'm printing them. Then what I'll do, if path is empty, so we can't do anything. If there is no path from source to destination, then what I'll do, I'll just find the largest path in terms of edges. First, what I'm doing, I am just finding the index of a path which has very less weight, like minimum weight. So what I'll do, I'll go to path weights, right? I'll find the minimum path weight and I'm finding the maximum path weight. I got the index. Now I have the path by smallest weight and path by largest weight just by the, like, paths will have the paths and path weights will have the weights, and then I found the index using weights array. Now I got the path using the paths array. Both of them will be having the same index because we are storing appending them parallelly. Next, I got the weight, minimum weight and maximum weight. Now what I'll do, I'll sort the paths based on the path size, that is number of nodes it visited. So I printed the path. The smallest one will be the zeroth index one and the largest one will be the last index one. And now I have to get the path of third largest path, that will be n minus k, because let's say first largest will be n minus 1, so the kth largest will be n minus k. We'll just check if there are more than k paths or not. Then what we will do, we'll just print this thing, smallest weight, largest weight in terms of edges, and then we will print path dot size of that path, path minus k path. It's very simple. Okay, we covered basic operations on a graph. In next session we will cover we will cover these things. uh, Next session we will be covering the little more advanced operations on a graph. Those are like, these were pretty basic. We will be covering three problems. Those are, first one will be getting connected components in a graph. Second one will be getting number of islands in a graph. Third one will be friends pairing. So these three problems you can like revise before the video comes, and just for like very quick revision you can watch the next video. Okay. Bye friends.